So today we're going to start with, we're going to introduce exponential functions. And so I want to go over a little bit of algebra, something that you've all seen probably a long time ago and may or may not remember. So the first thing I want to talk about is the graph of an exponential curve. A is the base, A is a constant, X of course is the variable. Now there's two possibilities for A. A can be greater than 1 or A can be between 0 and 1. A cannot be 0, A cannot be negative. That would be a problem. So that A has to be a positive number. It has no meaning mathematically. If A was negative, then all your output would be imaginary. Okay, so A can't be 1 because 1 to the X would just be a horizontal line. So if A is greater than 1, then we know we get a curve that looks like this. If A is less than 1, then we know we basically get the mirror image. So this would be A is between 0 and 1. So in the first case, we would call this one exponential growth. In the second one, we would call this exponential decay. It's actually that simple. So if things are growing, right, I've got the bacteria in the petri dish, doubling every 4 hours, that kind of thing. It's going to have this sort of thing. Something dies and it starts decaying. Get this thing. So those are both examples of exponential growth or decay. So so we remember the nature of an exponential graph, I want to introduce you and reintroduce you to this. So now we're going to do an application from Calc 1, or excuse me, from algebra, actually way before Calc 1. And I want to talk about, it's a money problem, a simple investing of money problem. Now there is one formula for investing. If you're talking about, you're going to grow at a certain interest rate for a certain amount of time and so on, it's called periodic growth. The formula for periodic growth is the accumulated amount equals principal times 1 plus r over n to the nt, r being the interest rate as a decimal, n is the number of times per year you're compounding, and t is the number of years. This formula has been around for centuries, actually thousands of years. This formula, believe it or not, is biblical. That's never changed. There is no such thing as, you hear simple interest in a pre-algebra class. There's no such thing. There's no such kind of situation where you put money in for a long time or you borrow money and you only calculate the interest at the very end. No, interest always grows. That's it. So if you're paying off your mortgage, you're paying off a credit card, whatever, there's always going to be interest accruing. Now, is the interest calculated annually? Is it calculated quarterly? Is it calculated monthly? Is it calculated daily? All of those things will change the amount of money. So again, P is the principal, R is the interest rate, N the number of times per year, T the number of years. So here's what we're going to do. We've been catching up on our old Sopranos episodes and watching, and we realized, if we're going to make it in this world, we're really going to have to become loan sharks, because loan sharks, well, that's probably the easiest way to accumulate wealth over a short period of time. So I'm going to set up a situation. We're going to start loaning out money. Nate's going to be my accountant, and of course, William's going to be the muscle, so that they don't turn in the payments on time and so on. So here's what we're going to do. Like any good loan shark, we're going to loan $1 million. 1 million because it's a nice round number that's easy to work with. And of course, like any good loan shark, oh my gosh, our rate will be 100%. That seems like a no-brainer. And we're going to talk about just 1 year. So with that, then the only question is, how many times per year are we going to compound the loan? So if I compound it, well, if I just collect at the end of the year, that means there's just one, or I could do it every 6 months. I could do it every 10 minutes, whatever we want. So we're going to make a little table here. And we're going to have N and A. And let's try different values for N just to sort of see what's happening here. So if I just did it once at the end, maybe I do it quarterly, I do it monthly. Let's say I do it daily. Okay. And just for fun, if I do it daily, whoops, hold on, 365 times 24. That's hourly. Okay. And then let's do it 1 million times. That's about every 30 seconds. Now, that will put a great deal of stress on Nate, of course, because he'll be emailing our client every 30 seconds, telling them what their new interest is. And then 30 seconds later, but anyway, we want to see what is happening to the accumulated amount as I increase the number of times compounding. And this is why you'd need a calculator, because we're going to plug the numbers in. But to make it easier, again, I used 1 million. So in our situation here, the accumulated amount is going to be 1 million times 1 plus. Now remember, this is as a decimal, so this would be 1. 100% is just 1 over n to the n times 1 year. So that makes it, this is basically what I'm calculating, and I'm multiplying it by 1 million. So if I do n equals 1, that's easy. This is 2 million. Okay, piece of cake. Now let's do it quarterly and see what happens to our interest. I do it quarterly. Whoops. Try that again. The calculator just got stuck for a second. There we go. 2,441,406.25. Of course, good loan sharks do not, drop the interest. Now, going from once a year to 4 times a year, we made over $400,000 of additional interest. Yes. Now, one absolute, the more I compound it, the more money there will be if everything else stays the same. So we want to see what happens as I keep compounding it. Is this going to grow without bound or what? So now let's do it 12 times a year. And simple calculator, that would be 2,613,035.29. So it continued to grow, but you notice when I went from 1 to 4, I got over 400,000. 4 to 12, I got about 172,000. That's not nearly as big a growth. Okay, but let's go from 12 times a year to 365. We're going to now compound every day. We want to collect. You say, is that unreasonable? Actually, no. Your credit cards and your mortgage are compounded daily. You may not know that, but yeah, they're compounded daily. That's why if you pay them, if you owe money and you pay things off early, you pay less interest. So this obviously is going to go way up because I'm increasing it over 30 times as many times. So raised to the 365 power. Now I'm all the way up to 2,714,567.49. Hey, wait a minute. I went from monthly to every day. That's a 30-fold increase, and I only made $101,000 extra. That doesn't seem like a lot of for all the work we're going to put Nate through, with all the emails he's going to have to put out. It appears that it's slowing down, doesn't it? No matter what, this is always going to grow. So really the question is there an upper limit maybe? Maybe this thing will peak out and I don't know, let's keep going. This is every hour, just for fun. So 1 plus. Now I'm all the way up to, I went from daily to hourly. Again, that's a 24-fold increase. And I'm at 2,718,126. And oh my goodness. That's like $3,500 is all I got. All right, poor Nate. You're going to earn your money, Nate. Now, this is about every 30 seconds, just for fun. We're just going to go crazy wild here. All right, 1 plus. Now you know why I used $1 million. It makes the calculations easier. All right, well, clearly this should be out of control. Got all of about $150 more. So here's, you notice something about the numbers. The more I increase it, like this 7 is going to stay forever. The 1's going to stay forever. Eventually the 8's going to stay forever. What's happening is it's growing, but I'm fixing the decimal places. it's going to grow forever, but the growth eventually will only be in the decimal places. Eventually, I won't see a difference. So in fact, if throwing all caution to the wind, if I said, keep going, I want you to do it. I want you to compound the interest 1,000,000 times per second. Poor Nate, that's a lot of emails per second. I'm gonna go crazy wild on this. Turns out there is an upper limit. And approximately 83 cents. This would be the upper limit if I could do this, so it keeps going. So really, here's the question. What if I take the limit as n goes to infinity of this? Of all the limits that exist, have existed, and will exist, this is considered a number one. There isn't anything that's even close in terms of importance. This is the single most important limits in all of math and science. $1 million times 2.718. 2.718. Does anybody know what that number is? Yell it out if you know what that number is.
Euler's.
I'm sorry, it's what?
Euler's mathematical constant.
I'll give you a hint. It's a letter of the alphabet.
Is it E? Is it the natural log?
E.
It's the number E, which is approximately 2.7 to blah, 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 blah. It's E. That the number E is considered the single most. By the way, what about pi? E is infinitely times more important than pi, or more used than pi. Pi is a number that shows up, circles and spheres and all that. E shows up in everything. This limit is E. Now, most textbooks will tell you this is defined as E. They'll say, every textbook will say, this is the definition of E. That's sort of true. Right now, in other words, this constant, we call it E, but it turns out this can be calculated. This limit actually can be calculated. This isn't a definition, this is a calculation. But for all practical purposes, when I see this limit, I know it means E. Next semester, we're actually going to calculate this by actually evaluating a limit. It's kind of a cool thing, but that's next semester. So, excuse me, if I could continue compounding. Now, the thing is, periodic growth means that I have fixed periods of time. Now, those time intervals can be very short, as we saw, but it's still fixed time intervals. If you went to the bank and you say, I'm going to withdraw all of my money today. So you go to the bank and you see a long line, you go, oh, good, there's a long line. That means by the time I get to the front of the line, I'll have more money because I waited in line longer. It doesn't work that way. Even if your bank can, calculate your interest daily, it's only once a day. It's not continuous throughout the whole day. There's periodic growth and there's continuous growth, and they're completely different animals. Periodic growth, fixed periods of time. Continuous growth means, 1 second later, I'm going to have more and it's going to keep going. So what happens is, if I take periodic growth and I take a limit as n goes to infinity, we get continuous growth. Continuous comes from a limit. So now we're going to jump over to the continuous side. I use this example so you can see the development of the numbers just using a calculator, and you see, man, this is looking more and more like 1,000,000 times E. Why is this looking like 1,000,000 times E? Because this is turning into E as n grows without bound. That's why. So it's kind of a cool thing. So E, and very specifically the exponential function e to the x, is what we're going to study next. So we're interested in y equals e to the x. Now, e being a number between 2 and 3, we know, therefore, it's going to have that upwards pointing curve. So we know that the graph of e to the x is going to look something like this. We know that because, again, e is greater than 1. And we said that exponential growth looks like that. Now, in terms of calculations, e is an irrational number. So if I was going to calculate it, of course, I'd need a calculator and approximations and all that stuff. I'm not interested in the numerical. I'm interested in the calculus part of e. For example, what's the derivative? This is a function and that is a variable. But what's different is this time my variable is in the exponent. Before, the variable was in the base and the exponent was a constant. This is a very different animal altogether. So our goal is, I want dy dx. I want, in other words, I want to take the derivative of this guy. Well, how do I take the derivative of this guy? Well, first thing is I'm going to show you a limit. I'm going to demonstrate it. I'm not going to prove it. I cannot prove it until next semester because there's a tool that we don't have yet. But if you think about it, last day, using implicit differentiation, I proved to you the derivative of x to a fractional exponent. We proved that last day using implicit differentiation, but we had accepted that truth earlier, that the derivative of x to the n is n x to the n minus 1 for all real numbers. We were accepting that even though I had only proved it for integers. Yesterday I proved it, or last day I proved it for rational numbers, but you had already accepted that as a fact anyway. I'm going to show you a limit that, and I'm going to show it to you, but I'm not going to prove it because again, the proof requires math that we aren't going to learn. My Calc 2 students on Wednesday of next week are going to see this limit proved. So they're not even there yet. And the limit is this. I'm interested in the limit, excuse me, as x approaches 0 of e to the x minus 1 over x. This is a very specific limit. So if I were to draw this on my calculator, on my graphing calculator, it actually looks like an exponential function. It looks like this. It's not going to move as fast as this one. It's going to be much, much slower. Why? Because I'm dividing it by x. So it's still going to look like this, except you're going, look at that going, wait a minute, hold on, hold the phone. This is not defined at x. So what ends up happening is, much like the sine graph when we did sine x over x, and we saw there was a removable discontinuity, but then we proved that that limit was actually 1. Excuse me. It turns out that this limit is actually 1. There's no functional value. I can't put e to the 0 minus 1 because that'd be 0. So e to the 0 minus 1 over 0 would be an indeterminate form, but it turns out the limit is 1. So if you do this on your graphing calculator, this is why I like the graphing calculator. If I do this on my graphing calculator, I'm going to see a graph that looks like this, and I won't see the hole because the hole is only at 1 point. And some of you would say, well, what if I just, again, to get an intuitive feel, you can't find a limit by evaluating. That's not possible. But you're saying, how do I know that this limit is 1? And how do I know this limit's not 0 or 1,000,000 or something? Well, one way I can do it is just, I'm going to evaluate this at a very small value just to see how close to 0 it is. That's not a proof, but that kind of, gives me an idea. So if I said, I'm going to evaluate this at, let's say, let's let x be, how about 0.0001? Let me use that. All right. So I've got 1, 2, 3 zeros and a 1 minus 1 divided by. My calculator says if I insert a value of 0.0001, then e to the 0.0001 minus 1 over 0.0001 is approximately equal to 1.000, 1, 2, 3, 4 zeros and a 5. Now, this doesn't prove anything, but it says, oh, okay, if I were to graph this and I'm plugging in values closer and closer and closer to 0, my y values clearly if I'm trying to graph it, are going to be really, really close to 1. So I am not going to do the formal proof again because the formal proof requires something we're going to learn next semester. And I'm going to make the statement. And in the TAN book, he does the same thing. He says, this is the limit. We're going to prove it later. But I need to use it now. And it really isn't a stretch because, again, if you graph this function on your graphing calculator, it appears to pass through the 0.01, even though it's not defined there. That's a removable discontinuity. That's a hole. But I need that value. So off to the side, let me put it up here. Again, I'm asking you to accept this without proof, although certainly circumstantial evidence, looking at a graph, messing around with a calculator. And again, the closer I get to 0 on my input, the calculator will give me numbers that are closer and closer and closer to 1. I'm going to see 1 point and a lot of zeros and another number. I'm never going to get the value of 1 exactly because I can't input a 0. So how do I find this? Definition of the derivative. So dy dx is the limit as delta x approaches 0 of e to the x plus delta x minus e to the x all over delta x. If I don't say anything else today, I've at least said one correct thing. Okay, that's the definition of the derivative. That's why we learned it. That's why we've been using it, because that's the only way I can get this derivative. You say, well, how am I supposed to work with that? Well, we know rules of exponents. We know just in general, if I said x to the a times x to the b, that's x to the a plus b. We know that. We know x to the a over x to the b is x to the a minus b. And we know that x to the a raised to the b power is x to the a times b. We know these. We learned these in intermediate, well, excuse me, probably in pre-algebra. Okay, so that's not even a question. Oh, so that guy right there, I can go backwards. I can write this as e to the x times e to the delta x minus e to the x over delta x. Okay, so I'm using a rule of exponents in order to pull it apart. We did something similar with the sine and cosine derivatives. We used expansion formulas to pull those apart. And once we pulled them apart, then we could factor. You see, both of these have an e to the x. And we know that the limit of a product is the product of the limits. So I'm going to pull the e to the x completely out. And that's what we'd be left with. So do a quick check. If I distribute the e to the x, I get that back again. So I know if I drop the word limit algebraically, this quantity is equal to this quantity, and this quantity is equal to this times this. Beautiful. Now what? Well, limit as thing goes to 0 of e to the thing minus 1 over thing. Limit as thing goes to 0 of e to the thing minus 1 over thing. It's the same thing, isn't it? So this limit is 1. That was the whole point of showing you that. What's this? Well, as delta x goes to 0, what's happening to e to the x? Nothing. There's no delta x here. This is just e to the x. So this is e to the x times 1. Whoa. So the derivative of e to the x is e to the x. Oh, that's kind of cool. So if I ask you the question, what's the derivative of e to the x here? E to the x, right. So the question is the answer. This is the only function that exists that is equal to its own derivative. And that has properties beyond fathom right now. So the derivative of e to the x is e to the x. Whoa. So let's mess around with this a little bit. So the very first thing we do is, what's the derivative then of e to a function of x? And remember the notation we use. It is implied that u is u of x. That's why we use the u notation. There's only one variable, x, so this would be a function of x. How do you differentiate e raised to a power? Well, it's the same thing. It's e raised to the power. Oh, but I always have the chain rule factor. So this is the formal form that you will always see. Now, if I just have e to the x, its derivative is e to the x. But what if I have e to the thing? And the thing is not an x. Then the derivative is e to the thing times the derivative of the thing. So let's look at that one. I want to take the derivative of e to the x cubed. Okay, so that is e to the x cubed. But that's not just an x. So I would then say times this, and remember that's called the chain rule factor. So the answer would then be 3x squared, e to the x cubed. The majority of time you're working with an exponential function, your argument's not going to be just an x. The majority of time you're working with trig functions, your argument's not going to be just an x. So that's why we have to remember where the chain rule figures in. That's why the chain rule is so important. Now, how else does E work? Well, let me erase this. What if I've got a product or a quotient involving E? I want to take the derivative of, let's keep it really simple, x to the 4th times e to the x. We'll take that derivative right there. Well, I'm going to have first times the derivative of the second. What's the derivative of e to the x? It's e to the x. Plus the second times the derivative of the first. That's it. That's easy. You actually will grow to love e to the x because it's the easiest derivative there is, pretty much. You know. So, well, what about the chain rule? Well, you always have the chain rule. They have the chain rule for every function. Now, we said we always want to write the final answer in a factored form. So what's common? Well, it looks like they both have an x cubed and they both have an e to the x, and that would leave me with an x plus 4. So that would be the best version of the answer. Now, if I asked you where does the derivative equal 0, you'd say, well, it equals 0 when x is 0. It equals 0 when x is -4. E to the x is always positive. E to the x is never 0, and it's always above the x-axis. So I would have two places where this equals 0. If I left it in this form, it would be harder to interpret. So what if I have this? I've got, let's say, the secant of x over e to the x. Now, I've mentioned before.
Wait, sorry, you're saying that e to the power x is no matter what going to be positive? I thought e to the x was just supposed to be representative of a constant, which is 2 point something.
E to the x is an exponential function.
Mm-hmm. But the out value of it.
An exponential function. I started the class.
Mm-hmm.
What does an exponential function looks like?
It is completely doubling no matter what. But then if we're
never touches an axis. No.
But if we're considering that in the function itself, that no matter what, that's always going to be positive, then we take that result and then we're multiplying it by the x. Is that what we're going for here?
You completely lost me with that last question.
Sorry.
E to the x.
If the function itself is separate from the value x, because what I'm saying is if the e is being derived separately, then that's no matter what going to be positive. Then if it's to a negative power, that's then wouldn't that be a negative or something like that? Versus the x is that's going to be inside of the function that's making.
Hold your thought. I think you're confusing everybody because I'm sorry.
Now, I'll ask you after. I'll ask you afterwards then.
I'm not sure where you're going with that. E is a constant. That's true. All exponential functions have a constant as the base. 2 to the x, 10 to the x, e to the x. Doesn't matter what it is. Constant is the base. The constant ain't changing. It's not a constant function. It's an exponential function. By definition, it has to have a constant as the base. You're not differentiating the constant. You're differentiating the function. The derivative of a constant is always 0. But a constant and an exponential function have absolutely no correlation whatsoever. One's the graph of a horizontal line. One is that thing that's going up. Yeah, they're as unrelated as you could possibly be mathematically. Yeah, you can't remove the e from the exponential. Now, remember I said before, anytime you have a quotient, if your denominator is something raised to a power, I'm not talking about a polynomial. I'm going to use quotient rule if I have a simple polynomial. But if my denominator is something raised to a power, it could be x raised to a power, then I said it's always easier if you rewrite this as a product. It is absolutely correct 100% of the time to use quotient rule on a quotient. But it turns out most of the time it might be easier to simply rewrite this as a product, and that would be e to the negative x. Okay? Now, that makes this is still an exponential function, but that's no longer an x. That's now a function of x. I have to consider chain rule. So when I do this, I'm going to get first times the derivative of the second. But what is the derivative? We'll do it off to the side. What is the derivative of e to the thing? It's e to the thing times the derivative of the thing. What's the derivative of negative x? Anybody? What's the derivative of negative x?
-1.
-1. And by the way, that -1 is really important. Yeah, if I lose the -1, then I've changed things. So this would be times e to the -x times -1. That's all I got to remember is, oh, that's not an x, that's a multiple of x. So I need the chain rule factor plus e to the -x times the derivative of the secant function, which is secant of x tan of x. So both terms have a secant, both terms have an e to the -x. By the way, the order you write them is really not important. I'll put the e first. I think it might be easier to read. And what does that leave me with? Well, here it leaves me with a -1. Here it leaves me with a tangent. So I can either write -1 plus tan, or I can write tan -1. I think most of you would probably rather write tan x -1. Okay. Now, question. Is this finished, or do I have to do something with this? It's kind of a trick question. My calculus is done, by the way. My calculus is finished. First of all, is this correct? Are these the same thing?
Yes.
Yeah, if I had left this as quotient rule, by the way, you know something really interesting? In quotient rule, don't I square the denominator? I didn't square the denominator. Well, actually I did. It's just, it turns out it would have factored and canceled. One of the reasons I rather use product rule, if I use quotient rule, there's actually a lot of algebra to simplify. Now, which one of these is better? The answer is yes. They're exactly the same. Wait, don't I have to put this downstairs? No. Why would you have to put it downstairs? Well, I thought you have to put negative exponents downstairs. You do. Negative x isn't negative. -5 is negative. Negative x is a function. Negative x is only negative if I put a positive number in for x. But what if I put a negative number in for x? Then negative x would be positive. You see, a function is neither positive nor negative. A constant is positive or negative. So, meaning you could absolutely leave this like this. That'd be totally okay. Don't confuse that. If I said e to the -x versus x to the -2. It is absolutely correct to write this as 1 over e to the x. It's absolutely correct to leave it. Because unless I actually put a value in for x, I don't have a negative exponent. Think of it another way. If I think of the number line, exactly half the numbers on the number line will make that number positive and half the numbers will make that number negative. So it's neither positive nor negative until I evaluate it. -2 is clearly a negative number. I'd have to write this one this way. I don't have to change this one because, again, that's a function, not a constant. So most folks would say, you know what, I'm going to write like this because it's prettier. But at the same time, well, this might be easier to work with. It doesn't really matter. If I were doing this on my calculator, I would actually enter it using a negative exponent. So both of these are correct. I'm not going to tell you one versus the other. And a lot of folks would give me the second one simply for the reason the original problem was stated as a quotient. So writing my answer as a quotient seems kind of consistent, but they're both absolutely correct. One is not considered better than the other. It's kind of like the comparison between a root and a fractional exponent. They're exactly the same thing, and you can choose whatever way you want. Just be consistent in your choice. Okay, so working with e's is actually very, very simple in general. There's just nothing weird about that, which is kind of nice. Now, e to the x is extremely important. E is an extremely important base, but it turns out the logarithms are even more important. Now, a logarithm, remember, is the inverse of an exponential. So let me remind you, because I want to remind you of the algebra before we do the calculus. If a to the x equals b, you put anything you want in there. You know, if 2 to the 4th power equals 16, if a to the x equals b, x being the unknown, a and b would be constants, then what does x actually equal? Well, x is defined to be the log, L-O-G, base a of b. The definition of a logarithm is the exponent. Okay, that's the definition. So let's write numbers down. So if I said 2 to the 4th equals 16, then the log base 2 of 16 equals 4, because the logarithm always equals the exponent. That's it. That's what a logarithm is. But logarithms are generally harder to work with because I can have a really happy mathematical statement, but figuring out what the exponent is in reverse can sometimes be a little bit taxing. Okay, it's not good or it's not bad, it's just what it is. So graphically, there's my y equals a to the x, assuming a is greater than 1. Now you guys remember about inverses in general. If I want the inverse of a function, the graph is the mirror flipped over the line y equal x. So what does the logarithmic function look like? So this would be y equals log base a of x. Okay, that's always true. So if that's the exponential function, then that's its logarithmic function. They go hand in hand. So if I have a point here, then I flip the x and y here. That's a reminder what an inverse function looks like. An inverse, basically you're swapping the roles of x and y at every point on the whole things. So an exponential function is never 0, it's always strictly positive, and the x-axis is actually a horizontal asymptote. Okay, very important that we know that. Never touches the axis. A logarithm, where this one grows very, very fast, this grows very, very slow. And it turns out the x-axis is a vertical asymptote, again, because of the whole flip-flop thing, meaning when I take a log of a number, I can get a negative value. There's nothing wrong with that. But what I cannot do is take the log of a negative number. The log of a negative number is imaginary, much the same as the square root of a negative number is imaginary. So we're only dealing with real numbers. So we will only deal with, you can take a log of a positive. So you're saying, how can a log be negative? Well, isn't it the case that 2 to the negative 4th power would be 1/16? Wouldn't that be true? So therefore, the log base 2 of 1/16 is -4. Oh, okay. So a logarithm can be negative because an exponent can be negative. But what I can't do is put a negative number in there. Why? Because when I raise a positive number to a power, I can never get a negative number back again. That's not possible. So remember that these go hand in hand. Okay. So I want to remind you of a couple of the log rules because we need those as well. I'm not going to do the derivation. I would in an algebra class, but I'm going to just go over the rules. If I said log base a of x plus log base a of y, I have log base a of x minus log base a of y. And the most important and by far the most used, the log base a of x raised to a power. Okay, these are the three main ones we look at. There are other ones as well. The sum of the logs is the log of the product. Now remember, what does the logarithm equal? The logarithm equals the exponent. Okay, so this one here kind of mirrors the whole x to the a times x to the b is x to the a plus b, because those are the exponents. When you add exponents, it's because you multiplied things. So when remember, the log is an exponent plus the log of an exponent, something got multiplied. That's sort of the mirror. Here, the difference of the logs we know is the log of the quotient. In much the same way as if I'm taking an exponential thing, to take the difference means there was a quotient somewhere. And the last one, which is by far the most important one, this n here, it makes that sound, it crashes. And that's n log base a of x. The exponent comes down and multiplies the logarithm in much the same way. When I'm raising to a power, I multiplied to get there. They're kind of mirrors. This is the main one that we use when we're manipulating logarithms. So what that means is if I have, just in general, if I had the log base a of, let's say, the square root of x, well, that's the same as saying the log base a of x to the 1/2 power, or 1/2 log base a of x. There's a simple rule when it comes to logarithms. You never actually have to work with the log of something raised to a power, because the power can always come in front as a coefficient. And we consider this simpler than this. And across the board, we would always rather work with this guy than this guy. Okay, it's just easier to work with. And I'm not talking about calculations. I'm talking about from function standpoint. So those are some of the reminders about logarithms. A couple of really simple notes. And also for all logs, remember, the log base a of 1 is 0. That's really important to remember, because on the graph of the logarithm, again, that's where it crosses. It crosses here at the point 1, 0. Oh, okay, that's right. Yeah. Okay, that's really, really important to remember that one. Just like an exponential function, when I raise it to the 0 power, I get 1. The log of 1 gives me back the 0. That's a really huge one, regardless of the base. Now, again, that base has to be a positive number, just like the exponential function. So with all of this said, why are we going over all this? Because the most important log, turns out, outside of chemistry, right, when you're doing pH and things like that, outside of chemistry, the only log you ever actually use in any conceivable capacity is the natural log. The natural log, which we write as ln. People say, ln? Well, we write log as log, so we write natural log as ln. I like it. Some people say, well, is that like log natural? No, ln is actually log Napier. Napier was a natural scientist who did a lot of the work and got named after him. But we don't say Napier log. We just say ln. Natural log, I know it's backwards. The natural log ln, so ln x is equivalent to log base e of x. We just never write it this way. Okay, it would be absolutely correct, but we never do. And on your calculator, you have an log key and you have an ln key. Now, the confusing thing is, universally, if I said log of x and I didn't put a base, if I didn't put a number there, does anybody know what the default is? What base we're automatically working with?
10.
10. So if no base is written, it's base 10. So you never write a 10. You go, why? Well, if I wrote the following, if I said cube root of x, 4th root of x, oh, I forgot to write something. What is it automatically? I didn't put it.
2.
It's automatically square root. We don't write the 2. Square root's the default if I don't write anything. I wasn't there when the rules were made. It seems to me that this would be far more consistent. We just don't. Now, the reason we don't bother, this is called, okay, that's called the natural log. What's that one called? There's another word we use. Anybody know? If you had chemistry, you're probably more familiar. We call it the common log. It's like common log. Well, yeah, because our number system is base 10. That's why we call it the common log. If I'm talking about pH balance in chemistry, if I'm talking about Richter scale, if I'm talking about decibels, that's a sound scale. They're the only 3 that I know of. Those are all log base 10s. The Richter scale, the magnitude of an earthquake, is a logarithm. Oh, decibels are logarithms. pH, right, something more basic, more acidic, is a logarithm, okay, which refers to exponents of things. So those are important to know, but everything else you'll ever do, especially things like exponential growth and decay, it's always log base e. And part of it is because how important E is, but also the calculus of E is much easier than any other base. The derivative of e to the x is e to the x. But what if I said, what's the derivative of 6 to the x or 10 to the x or 2 to the x? It's not the same thing. It's more complicated. We're going to go over that. But e to the x is wonderful. So here's what we want. I want, if y equals the natural log of x, I want to find dy dx. Okay, I want the derivative of the natural log. It turns out of all of the derivatives that exist in the history of the world, in the future of the world, and currently I looked ahead and behind, the second most common function to differentiate is actually a natural log. The number one would be a polynomial type. Natural log is the second most commonly differentiated function. It's actually that important and that huge. So we need a really nice handy formula for natural log. Well, if I consider, okay, let's think definition of the derivative, right? That's a beautiful way of looking at it. Then it would be the natural log of x plus delta x minus the natural log of x all over delta x. Well, I can't expand that. There's no rule for log of a sum. The sum of the logs is a log of a product, but the log of a sum, there isn't, I can't expand that. I can try to write that as the log of a quotient, but you know, I'm kind of dead in the water. Now, remember when we did the derivatives of tangent, cotangent, secant, and cosecant? We didn't use the definition of the derivative. We used our prior results of the derivatives of sine and cosine. Can I use a previous result to get the derivative of the natural log? Yes, I can. I can use my result of e to the x. You say, how? But log and e to the x aren't the same thing. No, they're not. They're inverses of each other. And it turns out most of the rest of the derivative formulas that we come up with, like the inverse trigs and things like that, most of the rest of our formulas will involve the fact that we already know something and now we're going to be looking at its inverse. So the derivative of an inverse is actually very, very friendly. So let's write it like this. If y equals the natural log of x, then what does x equal? Anybody want to try that? If y is the natural log of x, then what does x have to equal? So I'm working backwards. If it helps you think this is log base e, I'll give you a little hint. If I said log base 3 of 9 equals 2, that's a true statement. Could you write this now as an exponential? Yeah, this is true if and only if 3 to the 2 equals 9. Base to the exponent equals 9. What's the base here?
E.
So e to the y equals x. That's how it goes back and forth. As an absolute mathematical statement, if you're given a logarithm, you can write the exponential. If you're given an exponential, you can write the logarithm because you're using the same values, you're just rearranging them. Again, so I'm using all the same values. Log base of equals base to the exponent is that's an absolute. So if this is true, then this is true and vice versa. These statements say the exact same thing. The thing is, here I'm writing y as a function of x. Here I'm writing x basically as a function of y. I want dy dx, which means I'm going to differentiate this one implicitly. This is why we learn implicit differentiation. Not for the goofy problems we did the other day. If we never use it again, we're going to derive the second most important derivative that exists. And the only way we can do it is implicitly. So I'm going to differentiate both sides of this with respect to x. So I'm going to do d dx, All right, that's what we're going to do. Well, okay, I'll do the left side, you guys do the right side. 1. Okay. That was my contribution. So what's the derivative of the right side? Isn't this e to the thing? So what's the derivative of e to the thing? E to the thing. But we're not done. Times its chain rule factor. What's the derivative of y?
dy dx.
dy dx. Beautiful. We're done with the calculus. So this would mean that dy dx is equal to 1 over e to the y. So the derivative of the natural log of x is 1 over e to the y. Oh, wait a minute. Don't I kind of want something x-ish over here? Yeah, the derivative of the natural log of x, I don't really want a y. And gosh, so what are we going to do? Oh my gosh. The derivative of the natural log of x is simply 1 over x. Not because I told you, because we just figured it out. And I go back to this statement here. If x equals e to the y, then the derivative would be 1 equals e to the y dy dx. But if x is e to the y, then all I have to do is put the x back, and I get this result. Now that seems almost crazy. Wait a minute, I'm gonna have an exponential function, a logarithmic function, and the derivative of the logarithmic function is just 1 over x. There's no log in the derivative, there's no exponent in the derivative, it's just simply 1 over x, which is, well, if nothing else, is a little bit weird. So let's write that down, lest we forget. And then I'm going to show you something that might help make it more sense. So the derivative of ln x is simply 1 over x. But it's pretty much certain that you're rarely, if ever, going to take the derivative of the natural log of just an x. You're going to take the natural log of a function. Pretty much every time you're working with log, it's going to be log of a function for the most part. So how do I differentiate log of a function of x? How do I differentiate the log of, again, u of x? Well, how about 1 over u to start? But if u is a function, then at some point I need its derivative. So times du dx. And it turns out that one's going to be really handy. If you are taking business calculus, Math 121, that's calculus for people who hate math, as far as I'm concerned. They don't do limits, they just do formulas. The only derivative formula you really use in that one, besides differentiating x to a power, the only one you use is log. And it turns out that's the one in the business calc sense you use the absolute most often. You use logs more than regular things because of the nature of the kind of stuff you're looking at. So it's a good one to know. Now let's see if that makes some sense to us. Let's do something really simple. If I asked you to differentiate x to a power, we all know we're going to get x or nx to the power minus 1. And I can do this for any real number. Okay, so therefore I can get back any result. Tell me, is it possible, is there, what n, put it this way, what n gives 1 over x as a result? See, if I differentiate x cubed, I'll get x squared. If I differentiate x squared, I'll get x. If I differentiate x to the -3, I'll get an x to the -4. I will always get an x to an exponent of degree 1 less. So what would I have to differentiate to get 1 over x? X to what power would I differentiate to get 1 over x?
0.
But if I differentiated x to the 0, that's the same as differentiating the number 1. And what's the derivative of 1?
0.
Meaning there is nothing that I can differentiate. That's the only one I can't get. Again, because think about it this way. If my result were going to be x to the -1, that n would have had to have been a 0, which means my answer would have been a 0. It's not possible to differentiate x to a power and ever get 1 over x. 1 over x is the forbidden fruit. It's the only one I can never get. Now we know where the 1 over x comes from. The only way to get the 1 over x is to differentiate a natural log. If I asked you, how can I get x to the 7th? We'll differentiate an x to the 8th. Oh, okay. Every other exponent, you can tell me where it came from. But this one comes from here. Isn't that crazy? It's the only one that comes from somewhere else. So if I'm differentiating something involving a log, it's usually going to look something like this. Let's go simple. I want to differentiate, let's say, the log of the sine function. Okay, that should be 1 over the sine function. Oh, times the derivative of the sine function. Okay, can't forget that part. That will be a killer if I forget that. Well, what's the derivative of? Oh, is that right there? Yeah, times the, not the. Sorry, let's try that. I already differentiated the sine function. Sorry, gave away the punchline. Okay, what's the derivative of the sine function? Obviously, the cosine function. 1 over sine times cosine. Wait, that's just cos over sine. But what's cos over sine? Cos over sine is
Tan.
Cotangent.
Oh, hold the phone. Okay, wait a minute. We learned all 6 trig functions derivatives. We learned how to differentiate sine, cosine, tangent, cotangent, secant, cosecant. But only the derivatives of sine and cosine produced sine and cosines. The derivatives of all the other guys, like the derivative of tangent was secant squared. The derivative of secant was secant times tangent, right? The derivative of cotangent was negative cosecant squared, and the derivative of cosecant was negative cosecant cotangent. There was no derivatives that gave me just a tangent, just a secant, just a cosecant, or just a cotangent, if you think about it, right? Only sines and cosines could I get by taking derivatives. I got, again, I got secant squared, but what would I have to differentiate to get just secant? What trig function would I differentiate? There isn't one. It turns out the way you get the other 4, you have to differentiate a logarithm. And that is so cool. The only way you can get secant or tangent or cosecant or cotangent is to differentiate the log of something. Isn't that wild? Say, whoa, that is so cool. All right. For example, I want you to differentiate. How about the log of the secant function? This is going to turn out to be a hugely important result later on. Let's see, what would that be? Now I'm going to show you a little shortcut. You all agree that that's a good starting point? Would there be anything wrong conceptually? It is always 1 over u times the chain rule factor. Wouldn't that be the same as putting that in the numerator directly? Would there be anything wrong with that? Anybody? What's the chain rule factor? What's the derivative of secant? Blurt it out. You guys all know it. What's the derivative of secant?
Secant tan.
So I'm going to write 1 over secant times secant tan, and then in the next step, I'm going to write secant tan in my numerator. Or could I just, this is my point, can I just go ahead and put it in my numerator right then and there? Yeah, you can always do that. It's 1 over secant times secant tan, which is the same thing. Oh. And that's how you get a tangent function, is you differentiate a logarithm of a secant. I don't need you to remember where it came from. I just need you to understand that the logs are how I'm going to get all the other trig functions. Very convenient. And here's why. In a few weeks, okay, we've been doing the whole Jedi thing right now. We've been working with the light side of the Force and all that. But around week 8, week 9, we're going to switch over, right? We're going to go dark side. Oh yes, we're going to start talking about the anti-derivatives. I call it the dark side of calculus, but it's the funner side of calculus. And it's the where did it come from part of calculus. Where does the tangent function come from? Now you know. Where does the cotangent function come from? Well, now you know. I mean, we're going to work backwards. Okay. And the working backwards part is actually, when people say, what is calculus formally? It's actually the other way, the anti-derivative. That is actually the formal definition. I know William asked that question before. All what we're doing is calculus, but the word calculus actually refers to the anti-derivative part, which comes somewhere in the middle of the course. So when we master in one direction, then going backwards actually is not very hard. Okay, it really isn't. If I think derivative being left to right, then anti-derivative is just right to left. I don't need you to worry about those yet, because we still have most of our derivatives still to come. Okay, so the derivative of a logarithm is extremely useful. So let me show you something in general that's really, really important. I want to differentiate the natural log of x to a power. And I'm going to show you two ways of doing this. And it's very important that we understand this. Now, I love to use previous things that you've been exposed to demonstrate calculus. For example, when we prove the fundamental theorem of calculus, which is often considered the most important work in human history, there is no E equal mc squared if you didn't first have the fundamental theorem of calculus. So you could argue which one's more important. There's no Green's theorem in Calc 3, which is sometimes equated with almost equal. You don't have it without fundamental theorem. And when I prove the fundamental theorem of calculus to you guys, I will use the garbage pit in the first Star Wars movie where the walls are closing in, because it's the only way I can prove it. I will make many references to particular movies, and today I'm going to make one of the more important references. And some of you may or may not remember, it was the Rudolph the Red-Nosed Reindeer claymation, came out probably in the early 1960s. Yukon Jack, Abominable Snowman. Some of you guys may remember that. Every year it plays at Christmas for a few weeks, and it's actually, the whole point of that movie was actually based on this. It's based on differentiating this function, and I'm going to show you exactly where it comes in. One of the most important ones in Calc 2, it's the scene in the third Indiana Jones movie when the knight, and the bad guy is going through all the chalices and which one is the one that Christ drank out of and all that. And then he, like any Indiana Jones movie, he shrivels up and dies. And the most important line when he says, he chose poorly. It's actually a calculus reference because there's a chalkboard in the back where the guy had done a calculus problem and you had choices to make. And I'm pretty sure that's what the whole point of that movie was. It's always about calculus. And my favorite, of course, if you saw the last Avengers movie, Endgame, they talk about eigenvalues. That's what I teach in linear algebra. The whole point of that movie was based on linear algebra and understanding matrix theory and all that. It had nothing to do with aliens from outer space. It was math. So cool. I cried. Okay, so we're going to do this. It's 1 over x to the n times the derivative of x to the n. That's 1 over x to the n times n x to the n minus 1. Now, is there some canceling that takes place here? That exponent is exactly 1 less than that exponent. So doesn't that leave me with exactly 1? Does everybody see that? That's what I'm left with. How interesting.
Can you go through that one more time? Just that little process. The last step that you did with the exponents.
Well, that exponent's exactly 1 less than that exponent, which means I'm going to have a power of 1 on the bottom. Put a number in if it helps. If that's x to the 10th, then that's x to the 9th.
Because technically that would be on the top, and then they would just cancel out, right?
Yeah.
Okay.
Yeah, this is always going to be 1 less than this one. Now, could I have shortened this process? Claymation version, Rudolph the Red-Nosed Reindeer. Okay, it's spoiler alert, but it did come out probably before your parents were born. Yukon Jack and Abominable Snowman get into it. There's a little bit of fisticuffs. They go over the edge of the cliff. And kind of like when Blue the bear gets mauled by Shere Khan, every kid's crying at this point. Until later on, you realize that they're both fine. Because the exponent in this particular term is essentially the Abominable Snowman, which, by the way, he actually has a name. My wife actually has this little claymation figure of him. His name is Bumbles. And the reason they survive, if you guys remember, does anybody know the reason they survive? You discover at the end of the movie that Abominable Snowmen bounce. Who knew? This is Bumbles. This is Abominable Snowman. First of all, using rules of logs, and it bounces completely out of the statement because the derivative of a constant times a function is a constant times the derivative. So if I'm doing this problem right, I work this n completely out of the statement as a coefficient. Yeah, you didn't know how much calculus was in kid movies. There's a lot of calculus. I mean, come on, Snow White and the Seven Engineers, the quotient rule, That's where it comes from. So this becomes n times d dx. I know you think I'm weird, but so do my kids. This is absolutely equal to this. But this is just n times 1 over x. Way easier to get it this way than this way. So as a simple rule of thumb, if you have log of something to a power, bring the power in front first, then take the derivative because it'll be easier every time. So let's do an example of this. You said, well, wasn't that an example? Let's do something more complicated. I'm going to do a problem 2 ways. I'm going to do one the formal way and one the easy way. I want to take the derivative of the natural log of the square root of, let's say, 6x squared minus 8x plus 3. Okay. All right, so what do I do? Well, first thing is we're going to write this as, this is going to be 1 over the square root of 6x squared minus 8x plus 3 times the derivative of square root of 6x squared minus 8x plus 3. All right, this is absolutely correct. The derivative of log of thing is 1 over thing times derivative of thing. Well, obviously, I'm going to want to make that a exponent of 1/2. That'll make it a little easier to interpret. So this is 1 over the square root of 6x squared minus 8x plus 3. Now, what is the derivative of this? See, I haven't had, by simply writing 1 over, I haven't done anything. I'm just writing down what the derivative is. I actually have to take the derivative at some point. So that would be 1/2 6x squared minus 8x plus 3 to the negative 1/2. And now I have to take the derivative of the inside. That's my chain rule factor in continuing. So that would be what? 12x minus 8. All right. So on top, I've got 1/2 of 12x minus 8. On the bottom, I've got 6x squared minus 8x plus 3. And then I've got this thing to the 1/2 power. All right. Everybody good? We're done with the calculus. Now we just got to clean up this mess. Now look at top. Can I distribute that 1/2? I think I can. That would be 6x minus 4. Square root, thing to the 1/2. Can I combine them? Yeah, they're both square root. Ah. And unless I can factor the denominator, I'm done. All right, cool. Well, that wasn't that bad. That was way too long. I'm sorry, that's just way too long. I'm far lazier than that. You see, we know we got to write this to the 1/2 power at some point. What if we had done the problem this way? Okay, we all know that that's correct. But we're not thinking abominable snowman right now. We should be. If you got nothing else about the abominable snowman, that 1/2 bounces right out of the statement. So without doing any calculus yet, my original question is equal to this. I haven't done anything yet. Huh. All right, so what's my answer? Derivative of that. We're done. This is the way you should always do it. If I ask this question on a test, everybody's going to do it that way, and most people won't get the right answer because they'll get lost in the process. Anybody does it this way, gets the right answer really, really, really fast. Our goal is to get the right answer, and really, really, really fast is always a good thing. If I have log of something to a power, I can bring the power in front as a coefficient. I said that is the single most important logarithmic property. And that's the one you're going to find yourself using the most often, because when you're taking derivatives of logs, often it's going to be log of something raised to a power. So let's keep going. The tricky thing here is when you have a root, you don't always see that there's an exponent involved, but there actually is. Okay. And we don't want to miss that. Let's try another. What if, let's do something just, I don't know, downright creepy. Let's say y is the natural log of the cube root of the sine squared x. Okay. Oh, that was scary. I want to find dy dx. All right, guys, you're on your own for a moment. Okay. I'm going to pause this for a second while you're working. Oop, hold on, that froze on me here. I always forget to go back to the recording. So again, the key, before I do anything else derivative wise, I have to figure out, can I write this as something raised to a power? Once I do, now I can bounce the exponent completely out. No calculus yet. So this quantity and this quantity are identical. I now have log of a function. It's no longer a function to a power. If I had started the problem with putting an exponent on there, that's a piece of cake. You just bounce it out. But when you have the roots, you got to think about it. You say, okay, wait a minute, what am I doing? It's like Nate said, okay, I got a 1/3 here. I got a squared there. If you don't look at it correctly, of course, it's going to change your answer. I don't want to take the derivative of that. That looks way too much. That's too much. I want to take the derivative of that. So when I bounce it out, now my derivative is 2/3 1 over sine derivative of sine. Okay, 1 over sine derivative of sine. And now all of a sudden that problem wasn't so bad. And that hideous root only showed up as a coefficient. And we really, really like that. So again, if a logarithm is involved, a log of a function, your derivative is 1 over the function times the derivative of the function. But sometimes you can manipulate and rewrite things in such a way just to make it a heck of a lot easier. Now, one of the things we're going to do next day, it's the first concept on the next exam, is this concept of I'm going to take something that has nothing to do with exponents and logs and convert it into logarithms. I'm going to make it so that I have logs in the problem. And you say, but wouldn't that make it more complicated? Well, it turns out in certain situations, if I make it a logarithmic problem, I can actually do the problem much, much, much easier. And it's so cool. But I'm going to wait till next day to show you some of these things. There are so many properties of logs that can make complicated math very simple. And I'm going to give you a hint on one of them. Okay. You guys are all familiar with factorials. That's the exclamation point. So if I ask you to do 100 factorial on your calculator, unless you have TI-89 titanium like I do, you can't do it. It'll say error. 100? Seriously? You can't even do 100 factorial? What if I had to do 1,000,000 factorial or 1 bazillion factorial? Yeah, most calculators crap out at 69 factorial because 70 factorial is on the order of 10 to the 100th power. It exceeds the capacity of your calculator. Okay, but what if I had to do a really, really large calculation? How do I do it? Well, it turns out using logarithms. You can actually do, there is no upper bound to how big a number you could be if you're willing to use logarithms. And it's really, really cool. There are just some really cool results of using logs to answer questions. Now I want to do an implicit problem. All right. Let's suppose that e to the y equals x squared y cubed. Okay. Using implicit on exponential and logs is actually really handy and shows up fairly often. So I want to do this one implicitly. So this is what I want to do. Okay, I don't have a dy dx yet, so I can't say dy dx yet. There's a common mistake that people will start and say dy dx equals. Well, no, dy dx doesn't equal anything yet. I haven't actually found it. And I'm going to have a dy dx on both sides. So this derivative will be e to the y times dy dx. This is going to be straight up product rule. So first times derivative of the second, but that's function cubed. Okay. So, okay, mute yourself, guys.
Sorry, I had a question. Couldn't we just substitute the EY for X?
Nope,
since we proved that earlier, or no, it's a completely separate thing?
totally unrelated, yep.
Okay.
No, x does not equal e to the y in this case. That was because y equaled log x, that's why. All right, so first times derivative of second, so I have 3 function to the second power times derivative of function. I can't forget that guy. That will change my answer, but that's my chain rule factor, plus the second times the derivative of the first. Okay, now I want all the dy dx's on the same side. Usually putting them on the left just makes it a little bit easier bookkeeping. So that's going to be, think of that as 3x squared y. Don't leave the 3 in the middle. A coefficient has to be the first term. So I've got e to the y minus 3x squared y all times dy dx. I don't have to throw that over and then write it. I throw that over and write it at one time. On the right side, I have x cubed times 2 times x. So how about 2x y cubed? Again, that's the appropriate way because I have my coefficient first and then I have my variables in alphabetical order, which is actually technically the way we're supposed to do it. And so finally, dy dx equals 2xy cubed over e to the y minus 3x squared y. Beautiful. That was a piece of cake. Okay, that's nice. Am I done? Can I improve upon this answer? Ooh, can I let me improve? Well, I can't factor anything. Well, if I gave you ordered pairs, if I actually knew an ordered pair on this graph, okay, I don't know any values, but if I knew an ordered pair, let's just say, for example, if I replaced y, let's just say you replaced y with 2, then I'd have e to the 2 equals x squared times 8. Oh, I could figure out values of x that make this true. If you gave me a value of y, I could figure out values of x that make it true. That would probably be easier than trying to find x and then do y's. There's an infinite number of ordered pairs that you could right now tell me that all be icky and irrational and stuff. But if I want to find the slope, oh man, this be nasty. Can anybody think of anything potentially that you could do that might make this easier?
You can make that x squared y cubed and then factor out an x and a y.
Just stop there. Just stop there.
I'm sorry.
If I make it x squared y cubed, I will no longer have an e in that statement. And you're absolutely correct. That means the algebra will be so much easier. Now, most people don't even see that. It's right there. E to the y equals this stuff, and I have an e to the y in my answer. So why not replace e to the y with this stuff? And by the way, anytime you're doing implicit with an exponential function, you're going to find that's probably going to be the case that you can do some form of manipulation. It may be more trouble than it's worth. This answer is perfectly acceptable. But is it the most useful answer? No, I'm actually quite a long way from being the most useful. So what we're going to do is we're going to replace e to the y with exactly that. Now, remember, we always want to factor an answer. Now I can factor that denominator, but better than that, can I cancel something?
Professor, real quick, when you multiplied the y squared with the x squared, I feel like you dropped one of the exponents.
Oh, you're right. I did. Good catch. Good catch. So that should be. Hold on, make sure I got it. Good. Does that all work now? Yeah, I think that's good. Okay. I'm glad I got you guys working on this. I got all my editors are working for me now. You guys know I've fired all my staff. They're just doing a terrible job so far. Can I factor the denominator? Is there a common factor? There's a lot of stuff. What's common?
X squared y squared.
And that would leave me with y minus 3. Let's start with that. Now, can I cancel vertically? Well, let's see. What can I get rid of? I'll use a different color pen. I've got 1x, I've got an x squared, so I can take that x and one of these. Do you agree? I've got a y cubed and a y squared, so I can lose both of those, leaving me one of these on top. So my top, it looks like I have a 2y. I just canceled an xy squared, leaving me only an x. Oh my goose, look at that final answer. If I had to evaluate, that would be hard to work with. That'd be really easy to work with, wouldn't it? So far so good. I think we like that answer way better because I can factor and cancel. Now, is it legal to cancel? This is a tricky one. There's an absolute mathematically, you can never multiply or divide by something that can potentially equal what? Can never multiply or divide by something that can potentially equal, you want to try it?
Zero.
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 You'll always change the entire problem. So in baby algebra, when we were simplifying, we'd always throw in the disclaimer, an x can't be this number. I just canceled x's and y's. If either x or y could conceivably be zero, then this answer would not be correct. I would have just eliminated a huge portion of the possible answers. I have e to the y, which is a strictly positive quantity. Could x ever be zero if the quantity on the left has to be positive? No, x can't be zero. Can y be zero if the quantity on the left has to be positive? No, it
Yes.
cannot.
Oh,
No, because I have e to the 0 would be 1, but on the right side, I'd have a 0. So my
Right,
point
right.
is, because that statement that this quantity is always positive, neither x nor y could ever be 0. Is that a good thing? That's a great thing. That means canceling was legal. If either one of them could have been 0, then I could not cancel the ones that could be 0 because that's removing them. So this is the most useful, the best, the happiest, the cleanest, the easiest. This is the answer we would want. This is correct. This is way better. It'd be kind of like getting a really gnarly trig answer and then finding I could whittle it all the way down to something small. So I want to remind you of the whole 0 thing, because a lot of times we go through algebra, we're not always paying attention to that. So let me do a really, really simple example of something that you guys have, if I said solve, I want you to solve x squared equals, I don't know, 4x. If this were a remedial algebra class, you know what most students would do? It's like, duh, just go like that. And then what do you get? X equals 4. 4 squared. Yep, great. I'm done. I'm happy. Nope. You can't get any wronger. That's horrible. I made an egregious error, an astronomically large error. You can't do that. Why? Why can't you do that? Because x could potentially be 0. And I just divided both sides. I basically divided both sides by 0. You can't do this. This is terrible mathematics. Do calculus students do that? Oh, sometimes. The troublemakers do. No, there's only one way to solve this. And that's to factor. And what's my answer? X is 0 or x is 4. Oh, there are 2 answers. And when I divided both sides by 0, what did I do? I lost 0 as a solution. You can never multiply or divide by something that can potentially be 0. That's why if I have an equation, I can't just arbitrarily multiply both sides by a variable, because if that variable could be 0, now I'm adding solutions to the problem. If I'm dividing by a variable expression, I may be removing solutions. So the dividing both sides by x is absolutely illegal. That's not even a mathematical step, but people will try to do that. So in this example here, no, I definitely want to cancel, but am I removing things from the problem that can't be removed? No, because we decided neither x nor y can be 0, so they're canceled just fine. If either one of them could be 0, it'd be like doing what I just did here illegally, right? Canceling an x means I canceled. So that's not something that you have to dwell on. It's not something that's going to be a recurring theme, but every now and then they'll say, wait a minute, I'm canceling variables. Am I changing the answer if I do that? Basically, when I'm canceling, am I removing things from the answer? Okay, and you may be and unintentionally. All right. So if nothing more that today, being able to differentiate e to the thing and being able to differentiate log of thing. If you can do those, you are in good shape. Now you can go look at the practice test and notice there's some e's and there's some logs on some of the derivative problems. And now you know exactly how to attack those, whether it be e's and logs of functions or e's and logs in products and quotients where I'm using product and quotient rule. So all of that is good stuff. All right, so I will stop now